split new lectures, and I know Nima almost gave this one, but we'll give it.
Cool. Can you hear me? Is that all right? Okay. So before I start, let me thank the TASI organizers for putting together what looks like has been a very phenomenal and excellent TASI this year, and also thank you for inviting me to talk today. It's really an honor, and I don't take it lightly that I'm here to indoctrinate the future generations of particle physics. I should say on a personal note that I like Nima, actually never attended TASI. For no well, I was just confused at the time. I don't think I knew anything about the world, so I envy you all. I will say that this week for me has been like that the kid who kind of never had a birthday party when he was a kid, but finally attends one, but as the entertainment as an adult. So that's how I feel. So I think what I'm going to talk about has been kind of beautifully set up by Nima. I've been told by Ian and in conversations that it's kind of more of a phenomenological bent in the audience, which is great. But as a result, I'm kind of the assigned Sherpa to kind of take you into the kind of amplitudes lands of amplitudesology. And I think that's important because if you've looked at any of the amplitudes literature, you could kind of easily get lost. It's kind of a big place. Lots of things that are very formal, very technical, and if you kind of end up on the wrong side of the tracks, you could get scared and run away, and I've seen that. For that reason, I want to kind of outline at least some of the motivations for why you should care about scattering amplitudes kind of intrinsically. And I think a slogan which I once heard, which I thought was very much, I guess, the essence of the scattering amplitudes program is the notion that scattering amplitudes is an attempt at doing quantum field theory, but without fields. Okay. So what do I mean by this? Well, if you open any textbook in QFT, there's a very canonical workflow for how you do calculations, how you connect theories to experiment. And that workflow is that you write down an action, which is some local integral in space-time of some Lagrangian, which is some function of some field, let's say phi of x. Okay? You take this object, you put in all the interactions, compute the Feynman diagrams, compute, and then you're done. Now, one thing that Nima mentioned, and I think a lot of you already know, but I'm going to kind of harp on a little bit more, is that this story is incredibly powerful. But it has its own drawbacks. Now, of course, I have to kind of work it up a little bit, which is that this is so absolutely powerful that it basically has pervaded all aspects of physical science. I mean, this same procedure of quantum field theory works in string theory, high energy physics, condensed matter theory, stat mech, even economics, where things like Gaussian field theory actually has won the Nobel Prize. So I would say the gold standard for a powerful theory is that you can simultaneously explain microphysics and financially enrich yourself at the expense of others. So it's incredibly powerful. It's absolutely powerful. Okay. Now, at the same time, as you might imagine, this litany of compliments is about to proceed a kind of a takedown, which is that it has a massive redundancy. You've seen part of this redundancy, which is in the form of gauge invariance. Or in the case of gravity, diffeomorphism invariance. So for the case of the photon, there's a famous statement that you take a mu of x and you send it to a mu with some derivative of some theta. Or in the case of gravity, that you apply an analogous statement where these thetas and theta nus are completely arbitrary functions. Okay. So sometimes it's stated in maybe more classic literature that these are beautiful, infinite dimensional symmetries of our world. But as always, whenever someone says something is a symmetry and infinite dimensional, you should be suspicious. This is no exception. Of course, you all know that there's a reason why these symmetries exist, which is essentially that we wish to describe a set of degrees of freedom in a Lorentz invariant way, that is to say with mu and nu subscripts, simultaneously with the local action. Okay. And that at the same time is kind of working against the fact that we know fundamentally that the photon and the graviton have two polarizations in the case of 4 dimensions. Okay? So in the case of 4D, you know from general arguments about the little group that there's two polarizations. And yet this guy here has, at least manifestly from this 4 vector, 4 degrees of freedom, while this guy is a symmetric 4x4 tensor which has 10 degrees of freedom. So there's some massive overcounting which is occurring. Okay? And gauge invariance is precisely the way to essentially introduce lots of degrees of freedom and then remove them. So it's kind of a bait and switch to say this is a symmetry. It really is just adding a function, several functions worth of redundancy, and then taking it away and then asking for credit for it. Okay. Now, you know the outcome of this in terms of actual things you compute. Anyone who's computed, let's say, the 2-to-2 gluon scattering amplitude knows that there's a lot of terms. Okay? And that abundance of terms is not an accident. It actually comes from the fact that this gauge invariance imposes the ward identities that you know, which actually constrain many terms, relate many terms in amplitudes that you'd compute using this kind of conventional prescription. Okay? And this I think you're all familiar with. In fact, I suspect many of you have even seen this comparison of the Feynman diagram calculation for 3-to-3 gluon scattering versus other more elegant methods, and how that like hundreds upon hundreds of terms can easily collapse. And that's not surprising because there's a massive redundancy built into this description. Okay? So I think that's, for the most part, all pretty familiar. Maybe what's less familiar is that this redundancy is only the tip of the iceberg as far as the redundancy of quantum field theory. So to kind of beat that into you, let me consider a very innocuous theory, which you would naively say, well, it has no gauge invariance whatsoever, perfectly beautiful scalar field theory. Okay, so let's say I give you a theory of a scalar. Okay, so in fact, I'm going to make it a completely arbitrary scalar field theory. Okay, where k here is just some arbitrary function. Okay, so k phi, I'm going to keep, it's just going to, in principle, be some arbitrary Taylor expansion around phi equals 0. The first term will be a half for canonical normalization. The other terms, I'm just going to add arbitrary couplings. Okay, so this is a scalar field theory, so there's no gauge invariance. What you see is what you get. This should be beautifully, this should be some rich array of theories with random arbitrary couplings, filled with potential promise. There's going to be lots of interesting dynamics, surely. But let's investigate that claim. Okay, so it certainly looks like there's kind of an infinite number of parameters, any amount of complication. But the bottom line is that we should really compute some physical thing and ask, what is it in this theory? Okay. Now, what's the simplest thing we can compute? Well, the simplest thing we can compute, and really the essence of the S-matrix program, is to compute scattering amplitudes, because that's the only kind of invariant, a physical thing that we can use to extract information from this Lagrangian. So what will we compute? Well, just the 4-point amplitude. Just some A1, 2, 3, 4 for particles 1, 2, 3, 4. Okay, and this is relatively easy to compute. I'm going to drop combinatorial factors, but at 4-point we just have a quartic coupling here with a couple derivatives acting on it. You'll see that this is equal to the sum of pi dot pj, where I is not equal to j, just coming from these two derivatives. Okay. And so it's a quick calculation. Now let me define a couple. I'm blowing through these boards. Let me define the Mandelstam and Variants, which I'll use kind of ubiquitously in this set of lectures, which will be defined in the usual way: p1 plus p2 squared, p2 plus p3 squared, p1 plus p1 plus p3 squared. Okay. Now, this seems like an honest-to-goodness, perfectly fine amplitude. But you'll notice that this thing is proportional to lambda 4 of s plus t plus u.
So your convention is all.
That's right. Yeah. This will all be all in. Yeah. So I think in I won't be worried about all in versus all out, but everything will be either all in or all out. So I'm never going to be talking about in states going to out states. This will all be purely in states, let's say. Okay. Now, we'll recall that since this scalar field is massless, there's, of course, an identity, which is that s plus t plus u equals the sum of masses, which is 0 on shell. So this is 0 on shell. Okay. And it'll be crucial that we make that assumption. So whenever we talk about our scattering amplitudes, we're always going to be keeping two things in mind, which is that the sum of pi equals 0 and that pi squared equals mi squared, which are conservation of momentum and the on-shell condition. OK. Now, maybe this is surprising. It's vanished. OK. Now, as it turns out, you could just keep computing more things. Compute the 6-point amplitude, compute higher and higher. And at each step, you'll just keep finding the same thing, which is that the amplitudes keep vanishing. OK. What a strange puzzle. And if you were just at the mercy of Lagrangians, you would certainly find that this is some miraculous cancellation, some strange conspiracy. But there's, of course, no magic trick here. This is just us realizing that this formula for this theory actually describes a much simpler theory once we realize something, which is that physics is actually invariant under field redefinitions, appropriately defined, for the fields. Okay? So we can, in fact, define a field redefinition for scalars where phi shifts to some arbitrary function of phi, f of phi, subject to a condition that f prime 0 equals 1. Okay, so there's various ways of justifying this. But here's what the claim is. Take your Lagrangian that we wrote down, apply a field redefinition to it, and once you have that new action, compute the vertices, extract the Feynman diagrams, and the amplitudes will be the same before and after. Okay. Now, the reason why this thing keeps giving 0 is that this is actually a field redefinition of the free action. Okay, so in particular, if you just started with L equals d phi squared and applied this procedure for a sufficiently clever function f, you can build this k. Okay. Yeah, so this actually has to do with the fact that you want the leading term. So here's the physical way of understanding this condition. So this is a little bit pointillistic, but this is an expansion. And the reason why this field redefinition is fundamentally an invariance of the action is that when you talk about computing Feynman diagrams, you're doing a path integral over the fields anyway. Phi is an integration variable. Okay? So phi is not something that you actually end up. It doesn't end up in the scattering amplitude. The amplitude depends on the momentum. You integrate over d phi. And consequently, you can really think of phi as something you're integrating over. Now, that said, you have to make sure that your asymptotic states, when phi is far off at infinity, where you're putting insertions of your particles, which are then going to scatter, you need those fields to be properly normalized. So you need this thing to be a 1 here. Far from where the interactions are happening, these nonlinearities aren't important. But really, you can test this out, apply this to an action of your of your choice, and you'll find this miraculous statement. So what this means is that there's actually an even bigger redundancy than maybe you're used to thinking about, where gauge invariance and diffeomorphism invariance are actually just a massive subset. Okay, these guys shift in a very specific way, but if they're, if you like, just another set of field redefinitions that you could act on the Lagrangian. And at the same time, leaving the amplitudes, the things that you actually physically care about, entirely unchanged. Okay? Yeah?
Sorry, I don't know if you mentioned this, but what was the intuition for that vanishing? You said there was
yes.
make it go away, but
yeah. So in other words, imagine you take start with a free action and apply a field redefinition to this. Okay? So send phi goes to phi plus. Phi goes to f of phi. So in doing so, you'll find that there's a terms that look like d phi, and then f prime squared. Okay? So the statement is, for a sufficiently intelligently chosen f, you can then reconstruct this k. Okay? And this is well known in the case of scalar field theories. People discuss this in the case of the pion action and so on. There's many different ways of rewriting the same theory. So this is not intrinsically maybe that surprising of a statement. But it does tell you that there's an infinite dimensional symmetry if you believe in Lagrangians for all theories. Okay? You could do this not just for scalar field theory. You could do this for Yang-Mills, gravity theory. Just do any field redefinition you like, compute amplitudes, and you'll find they're miraculously invariant. So this is in some sense undercuts the original kind of belief you may have had that gauge invariance is special. Because not only are these not invariances, after all, the Lagrangian actually changes. The Lagrangian is not invariant. But in spite of that, the amplitude is actually invariant. Okay. So the kind of key point here is that we're missing something. I could have given you an action, written it this way, computed the Feynman diagrams, and I have a huge set of terms that all sum to 0, just like the set of word identities that fix constraints among the amplitudes. Yeah?
In what sense is it the same amplitude? Like you've redefined your fields, presumably the propagating degrees of freedom are now not the same as they were.
Right. So the key point is that this constraint that in the linearized order the field is actually the same was important for that reason. So if I had not started at linear order but some higher order or done some more crazy procedure, this would have failed, in fact. So that actually exactly talks to the fact that this has to be a weakly coupled theory where nonlinearities actually decouple at asymptotia where I actually start sourcing these fields. So indeed, we secretly have kept the asymptotic field the same despite the field redefinition. Okay. Any other questions? Now, this is all, I guess, a way to highlight the fact that anytime you get a Lagrangian, it could be a theory of one type or another. It's hard to tell. But the converse statement is actually even more terrible, which is it says that I could give you an infinite set of Lagrangians that all look different, all give different Feynman diagrams term by term, but all describe exactly the same theory. Okay, so this is an infinity-to-one mapping of Lagrangians to theories, as you might imagine, very much non-economical and hard to determine the space of all theories, for instance. Let's say you wanted to enumerate all possible quantum field theories. It would be very difficult to do this with Lagrangians for precisely this reason, this massive redundancy. Okay. Now, let's say that we take our cues from this argument and say, well, let's not use Lagrangians. What can possibly define a theory? After all, it would be irresponsible to deconstruct this without reconstructing something. And that's really where the Amplitudes program enters. Okay, let's write here. Okay, so what defines a theory? Okay. And implicitly, I mean, if not the Lagrangian, what defines a theory? Well, I think, again, kind of sliding into things slowly, let's imagine the following Gedanken sociology experiment. Okay, so imagine you have a friend who happens to live in some distant pocket of the multiverse with totally different physics than you. And you manage to somehow correspond with each other. So you enter each side of a two-sided black hole and manage to compare notes. And your friend tells you the following statement. Okay, my universe is much different from yours, but I can tell you one thing about it, which is that it's comprised of 8 massless particles. Let's say your friend told you this and nothing else. Well, 8 massless interacting particles, let's say. Okay. Now, the question is, can you now, with nothing else, compute the S matrix at tree level for your friend? Okay. And in what circumstances would it be easy or hard? Okay. Now, of course, it should depend on the identities of these particles, so a little bit more information is needed. Let's consider the possibility. So let's say it's a bunch of scalars. So if you've been properly indoctrinated by QFT textbooks, you'll think, oh, this must be really easy to get the S matrix. Of course, I just write down a Lagrangian. It's some simple scalar field theory, maybe some phi-4 theory. But you'll immediately realize something, which is that there's a huge amount of freedom in what you can write down. Right? So if your friend says that there's 8 scalars, there's any number of, let's say, quartic couplings you could write down, and you wouldn't be able to write down the S matrix because you wouldn't actually know any of these couplings or their ratios. You'd have actually great difficulty, despite the fact that operationally it'd be easy to write down the Feynman diagrams. Okay. Now, in contrast, if these 8 massless particles were actually vectors, as I'll flesh out a lot more deeply in a bit, you'll hopefully realize, well, recall the important identity that 3 squared minus 1 equals 8 for all values of 8. And this is precisely matching onto the 8 gluons of, say, an SU3 Yang-Mills theory. Okay? You might just be smart enough to realize that. And then you'd say, wait, I don't even need any more information. Up to a gauge coupling, I can just tell you the tree-level S matrix. Why do you know that? Because at least if you went through the usual Q of T story, you just write down the Lagrangian and realize there's no free parameters other than that one piece. So in other words, the Lagrangian is just some 1 over 2g squared trace f squared. Okay? Much less freedom than in the top case. Okay? So despite the fact that it's harder to do, it's actually, there's more, so in some sense, despite the fact that Feynman diagrammatically there's more terms, the theory is actually simpler because it has fewer parameters. Yeah. So in the case of the scalar case, I'm not assuming it's a gauge theory. Yeah.
There are additional statements that you are making.
That's true. So indeed, I'm refining the amount of information I'm given, and I'm asking whether if I told you it was a scalar versus a vector versus a tensor, whether you would have a sufficient information to construct it. So absolutely, I'm adding more information. For the scalar case, I'm saying if I was just told it was scalars, I wouldn't have enough information to know everything. That's all I'm saying. For the case of vectors, I would. Yeah. Then it is this theory. In fact, I'm going to derive this in roughly 30 minutes. So in 30 minutes, I'm going to prove that there is no option other than the gauge theory. So it's not even an assumption. No. Yeah, I'm assuming that. They're all interacting. Yeah. So they're not just free particles. Yeah, absolutely. In the last case, so again, the claim isn't just that I'm assuming that it's a gauge theory. I'm going to prove it shortly. If you had tensors, right, with the idea that these are maybe 8 interacting gravitons, you would know from various field theory reasons that, well, there's one stress tensor, one graviton, one metric. It wouldn't make sense for there to be multiple massless spin 2 tensors that are self-interacting. And you realize that your friend is actually lying because there's no way they could possibly have 8 of them. Okay? Again, from the field theory perspective, you have to make assumptions. You just have to say this is a gauge theory, this is a gravity theory. But we're going to prove all these statements, hopefully by the end of this lecture. Okay? That there is no option other than this. Okay? But there was a point to this little sociology experiment, which was that the point here is that spin matters. Okay? This is the kind of one of the crucial inputs to how we understand scattering amplitudes, which is that despite the fact that there's more gauge invariance in going from scalars to vectors and then to tensors, that the Feynman diagrams get more and more complicated. In spite of that, the theories are actually simpler because they have fewer parameters fixing them. Okay, indeed, we should measure the simplicity of a theory not by the number of Feynman diagrams we have to write down, but by the number of free parameters that actually fix the theory. And the fact that there's one here and one here, that is to say the gauge coupling in G Newton, is precisely why these are actually much simpler. Okay. And we're going to use this to our advantage in a bit. Okay, so this already tells us that we can actually make some statements without a Lagrangian. My claim is that these 2 statements will be derived. But let's discuss this a bit more systematically. So if you're an amplitudes guy, what have you, if not a Lagrangian? What fixes the theory? Sorry? Spinors is, that's, yeah, I should keep them as bosons, let's say. But we can do the same exercise, in fact. So a bit after this, I'm going to consider this for arbitrary helicities, in fact. Any other questions? OK. What are the inputs that we're going to apply? Well, there was a way to describe how kind of amplitudes guys work. It's that they want to use the kind of old Feynman method for solving problems, which is to think hard and then write down the answer. Except we need some constraints on the answer. So the idea is skip the middleman, forget the quantum fields. They're perfectly fine in their own right, but we just want to understand things a little bit differently. Then write down, if you like, an ansatz for the answer, and then constrain it with the actual physical properties you know that ansatz should actually satisfy. Okay? And these will not be statements like gauge invariance, because as I just said, that's an artifact. Okay? So there's a couple very simple statements that I need to include, like dimensional analysis. All I mean by that is just counting in derivatives, powers of couplings. This is not something that gives you have any value added as compared to Lagrangians. You can do all this at the Lagrangian level, but it just happens to be useful pragmatically for thinking about the amplitudes. It's a useful tool. So there's really no value added from this relative to the usual way of thinking about things. Second thing is Lorentz invariance. And in this case, I'm also going to include its kind of cousin, which we'll discuss in depth, which is the so-called little group. And this, to some extent, is something manifested by Lagrangians. We write things with mu subscript contracted and so on. But this little extra twist of the so-called little group subgroup of the Lorentz group will be actually crucial for a story. Yeah, I'll refrain from talking about it until a little bit. And then lastly, the statement of the analytic properties of amplitudes. Okay, so what do I mean by this? I just mean the fact that you talk about amplitudes as functions of external momenta. Okay, then there are certain statements familiar to you, like factorization, which dictate very specific singularity structure for the amplitudes. Okay? That is to say, when some intermediate particle has a momentum squared going to 0, in the case of a massless intermediary, then this thing factorizes into two separate amplitudes. Okay? So it's this type of procedure at tree level. It's called factorization. At higher loop level, we call this versions of unitarity, generalized unitarity, and so on. For the most part in this talk, I'm going to focus on tree level because I want to keep things nice and simple. Okay, good. So these are the three tools that we're actually going to use for the first two lectures entirely. Actually, nothing more than this. And our goal is to derive essentially as much of quantum field theory as we can without assuming anything else. Okay. So with that, let me briefly outline the three lectures, just so we have, now that I've finished my little spiel. I have three lectures. The first lecture, modulo what I've just discussed, will be about fundamentals. Kind of the lowest lying set of ideas you need to know to be literate enough to read maybe a scattering amplitudes paper. The second will be something I'll call tools, which will be about specific constructions that allow us to build the full S matrix at tree level for a variety of theories. And both lectures 1 and 2 here are very much kind of rebuilding things that have already existed. Right? We're not constructing new features per se for quantum field theory. We're just trying to understand kind of old features in a new way. The last lecture actually will be different from this. And there's really no other way to describe it other than sorcery, because it's absolute magic from the point of view of scattering amplitude. So I'm going to talk about things that go beyond what you could have already known at the level of the Lagrangian. And this, in my mind, is the most exciting part of amplitudes. It's the fact that there's any number of kind of miraculous formulas, relations, symmetries that are completely invisible to someone who works with Lagrangians. It's simply not even kind of an observation you can make for a Lagrangian, and yet is a property of the S matrix. Okay. Specifically, I'll be talking about something known as color kinematic duality, which is an amazing fact about not only gauge theories and gravity theories, but also various scalar field theories. And it's a quite ubiquitous fact about quantum field theory, which you would never know had you been dealing with fields alone. OK, any questions before I dive into things? OK, good. So, good. All right. so let's start with the fundamentals. So the goal for this lecture, let me just say, is that we want to construct all possible theories of massless theories in 4 dimensions, interacting massless theories in 4 dimensions. And we're going to do it from the ground up. Now, the first step to that is an incredibly useful formalism known as the spinor helicity formalism, which I'll now discuss. In other words, I'm going to start with kinematics. Kinematics is usually a topic that's given a pretty short shrift in the QFT. You usually think of it as, well, define some momenta p mu, p0, pi. No, define it. It's Lorentz invariant, construct invariance, and then once you're done with that, you can get to the real fun of dealing with interactions. Right? There's a very natural factorization in the usual way of thinking about things, where you have kinematics and then dynamics is kind of a separate story. The dynamics is all the interesting Lagrangian stuff that we've been talking about. Now, in the amplitudes business, there's actually many more different types of variables you can use that aren't just for momenta. Just to name a few, there's also use this, or you could use spinors, twisters, momentum twisters. So there's a whole array of different variables, all encoding very similar information. And the value added is that different ways of representing the same objects can manifest different symmetries. Okay, so this is something you know in any number of ways. But if you just use, there's no sense in which there's a wrong set of variables because they're all equivalent. But if you use the wrong variables, then your calculations will be much harder. Okay. Now, in the picture here, we're going to focus on the case of spinors. Something called the spinor helicity formalism, where the kind of extra ingredient that will help us a great deal is the Lorentz invariance in the little group. Okay. All right, so let's start. Let's just define it. So it's actually not too complicated. A definition. The essence of spinor helicity, the definition of spinor helicity, is to essentially take the 4 components of a massless vector, 4 dimensions, and map them into a 2x2 matrix. Okay, so how do we do that? Well, we can take p mu, dot in it to some sigma mu, alpha alpha dot, where alpha and alpha dot are, of course, the usual Lorentz indices associated with the spinor representations. Okay. Components, we can write this out in glory detail. P0 plus P3, P0 minus P3, P1, 2, P1 plus IP2. Okay. Here, sigma mu is 1 sigma I. Okay. So it's just a rewriting of the usual objects. I should say throughout I'm going to be using conventions where I'm in mostly minus conventions. Okay. But we're just going to construct all the kind of kinematic friends we have using these spinor helicity variables. Using we haven't introduced the spinors yet, but using this p alpha alpha dot. We'll see how spinors enter shortly. Any questions? Yeah. Yeah, that's right. So this the question was whether this definition is only true in 4 dimensions. This is true only in 4 dimensions, but there exist spinor helicity formalisms in lower and higher dimensions. So 3, 6, 10. It's in this sense, what we're doing is a little special. In fact, I would say, at least to me, I think the most elegant and geodesic picture happens in 4D. We, of course, live in 4D. But you can make similar statements in higher dimensions if you have the right formalism. Questions? OK. Very good. So let's say we just try to construct invariants out of P. Well, there's only one Lorentz invariant afforded to us out of one P alpha alpha dot, which is its determinant. We can't take its trace because that would contract alpha and alpha dot, and those are in different representations of the Lorentz group. So we have just that this thing is actually equal to P mu P mu. You can work it out yourself. Just compute the determinant of that matrix. And throughout this lecture, I'm going to assume massless. Okay? That's just going to be my assumption. Questions about that? OK, so there's a nice sense in which we have a Lorentz invariant of one particle, which is its invariant mass, which vanishes for massless particles. The place where spinors enter is the fact that, well, if the determinant of this matrix is 0, that means that it has at least one 0 eigenvalue. If you had two 0 eigenvalues, then it would be 0. Very much uninteresting. So I want it to have at least one non-zero eigenvalue and one 0 eigenvalue. Consequently, as a matrix, it has rank 1. Right? It has a null space that's one-dimensional. And any rank 1 matrix you can write as an outer product of two vectors. In this case, two-dimensional vectors, which we call spinors. So for the case of massless states, we can write P alpha alpha dot is lambda lambda alpha dot, where lambda alpha is a spinor and lambda tilde alpha dot is some anti-spinor. I'll often just call them lambdas and lambda tildes. Okay. Now, here's kind of a minor point that I should discuss briefly before blowing through, which is that if you demanded real momenta uniformly, then there would be a constraint between lambda and lambda tilde. Okay, and that's obvious because P alpha alpha dot is Hermitian for real momenta. Right, if these P's are real, then this is manifestly a Hermitian matrix. So what that means is if P is a set of real momenta, then this implies that lambda tilde is actually equal to lambda complex conjugate. So there's a relation between those two lambdas when you restrict to the real momentum slice. But as we're going to see, it'll be much more useful to move away from that slice and think of the S matrix as an analytic continuation away from real momenta, where at the end of the day, we can always return to the real axis if we please. Okay? In the circumstance where we have just random complex momenta, these are unconstrained. Okay? So there's a reality condition that relates these for real momenta, but for general complex momenta, I can think of lambda tilde and lambda as just completely independent two-component objects. Okay. All right. Now, very good. We can now construct the usual, kind of the obvious invariants out of these objects, which are the invariants you can construct from the spinors and the anti-spinors. Okay. So I'll kind of go through this quickly, but you can imagine taking lambda I and lambda j. So the spinors for legs I and legs j contracted against some epsilon tensor alpha beta. And this is equal to ij in our notation. So when I write down an angle bracket of ij, that just means the natural invariant constructed from these two objects. Now, one thing you need to keep in mind is while I'm saying the word spinor, you might think the words Grassmann, anti-commuting, and so on. But these are not anti-commuting objects. Okay? These are not spinors in the sense of literally fermions and inaction, which anti-commute. These are just two-component objects that are made of complex numbers. Okay. And likewise, we can define the analogous object. For the angle tilde lambdas, which we'll call square brackets in the usual way. Okay. Sorry. So the I and j indices here label different external legs. Okay. So we had just been considering one momentum here, but if I give you an amplitude, I have 1 to n, and that I and j just label different legs. Okay. Okay, good. Now, from these objects, you can construct the usual Mandelstam invariants. So Sij, recall Sij is the invariant mass of some pi plus pj squared, which is just 2 pi pj, because everything has pi squared equals 0. And this pi.pj is actually written nicely in terms of these angle and square brackets as just their product, ij. Okay, I won't go through why that is explicitly, but if you just plug in the components, you can determine this. So in other words, our usual friends, Mandelstam invariants, are just can be rewritten in terms of these angle and square brackets in a nice, simple, and convenient way. Okay. Good. So that's the essence of spinor helicity. Let me talk about this property, or really the symmetry of the little group, which is actually the reason why it gives you mileage. Okay. Hopefully you remember from your QFT, Weinberg QFT class that the little group is defined as the subgroup of Lorentz transformations that leave a particular momentum invariant. Okay. So let me be a little bit concrete about that. So you can imagine taking some momentum p mu. Let's go to 4 component for the moment. Go into a frame where it looks like it's just moving in the z direction. And just ask, what is the subset of Lorentz group generators that leave this object just invariant, straight up invariant? And I encourage you to look back in your Weinberg 1 and 2. The representations of that little group actually define the states in your Hilbert space. Okay, they give you the different spins, helicities, and so on. Okay, so the fact what we were saying before, which was that massless vectors are described by 2 degrees of freedom, and likewise for massless tensors in 4 dimensions, that is all derivable from this fact. Okay. But for our purposes, all we need to know is one thing, which is the little group is the set of transformations that leave momenta invariant. Okay, so the slogan here is that just this little group leaves a given momentum invariant. And we can construct that set of transformations using spinor helicity quite trivially. Okay. What is that? Well, for the little group, consider the following transformation. Take a given lambda I. Okay? It's some way of describing the external kinematic data. Now just send it to ti times lambda I, where ti is just some random complex number. Okay? A different random complex number for each leg I. And likewise, you can imagine taking lambda I tilde and sending it to ti inverse lambda I tilde. Okay. Now, why did I multiply this by ti and this by ti inverse? It's so that their product, which is the momentum. Okay, so I'm going to write this in. Pi is invariant because, as we saw, pi is just the product of these 2 momenta, so the t cancels. Okay. So the little group is a set of transformations which, when acting on lambda and lambda tilde, cancel when you write down the final momentum. Okay, that's the definition of the little group. Okay. Now let me mention one thing, which is actually can be slightly important, which is that for complex momenta, I can have these ti's just be random complex numbers. That's perfectly fine. But you'll recall there was a reality condition, and if you chose to have real momenta, then that reality condition turns into the statement that ti is a pure phase. So in other words, you want to rephase lambda by a phase and rephase lambda tilde by the opposite phase, since lambda and lambda tilde are complex conjugates of each other in the case of real momentum. But in general, for complex momenta, I can just keep these ti's as completely arbitrary parameters. Okay. Now, what does this buy us? Okay, so you might think, well, this is why introduce this formalism where you act with the symmetry and it ends up canceling in the end of the day in the momentum? Okay, what's the point of this if the momenta are invariant? And in fact, let's say you only had a scattering amplitude that depended only on PIs. Okay? For instance, a scalar field theory. Scalar field theory would have just be a function of Mandelstam and Variants, and it would be absolutely invariant under the little group. And you would learn nothing from this little exercise. And that's true, because scalars are in the trivial representation for the little group, and you can't learn anything from it for that reason. The value added for this actually comes from higher spin, precisely because higher spin fields live in non-trivial representations of the little group. Okay? Now let me be explicit about that and just remind you how the little group acts when we start dealing with particles that spin. And the extra ingredient, as you might anticipate, is that when we talk about spin 1, spin 2 scattering amplitudes, they don't just depend on P, they also depend on polarization vectors. Okay, so polarizations in terms of spin or helicity are actually quite simple. Let's imagine I just have a spin 1 vector, and I want to ask about the positive and negative helicity polarizations. Okay, so these are just vectors in my space, and going into spin or helicity variables, they're just given by alpha, alpha dot matrices. Okay, so we want to construct some alpha, which some set of epsilons, which have all the right properties to be polarizations. Okay, so let me just quote you the answer. It's actually quite simple, but already introduces an interesting new addition. Explain this shortly. Okay, so this thing is a bispinner constructed from two spinners. One is the usual lambda that was corresponding to the external leg that the polarization is connected to, and a new object, eta alpha. Okay, it's a new spinner. And likewise, a new spinner, eta tilde. Okay? Now, I just had to introduce these objects. For the moment, let me just imagine I pick some random eta and eta tilde. I just pick it. Now, given an eta and eta tilde, I can just check that this satisfies the usual properties of a polarization tensor, polarization vector. So let me even walk through it. If you imagine taking epsilon plus and dotting it into P, okay, just take epsilon plus and dot it into this momentum, then you'll see that this is proportional to eta lambda lambda lambda, okay, with some other denominator. Eta is also a spinner, yes. So it has an alpha index and alpha index. So eta and eta tilde are spinners and anti-spinners. And the point here is that this is 0 because it's anti-symmetric. Okay, so if you dot a spinner into itself, you get 0. Okay, so of course you can check this for E plus. It all works beautifully. But you should be upset because I just introduced a completely random parameter eta. Okay, pulled it out of a hat. Where did it come from? Well, this eta is actually the very first sign of introducing gauge redundancy into the problem. What do I mean by that? Well, the claim here is that I can pick any eta I want, and I'm going to get the same answer. So this is what's striking. The polarizations are clearly dependent on eta, but if we change eta, we're going to get the same answer no matter what eta is. How could I possibly say that? Well, let's change eta and see what happens. Okay, so let's take eta. And let me just send it to a new guy, eta prime. Keeping in mind that I can always write a spinner as a linear combination of any two other spinners, because they're two-dimensional. Okay, so there exists some A here, and then some B, where A and B are some proportionality constants. And I'm just expanding my new eta in terms of the old eta and lambda. I can do that. Now we can ask what happens to epsilon plus. Okay, so this guy goes to epsilon plus prime, which should be different. But let's see how it is different. So we have this plus b lambda alpha. Okay, just that shift in the top, and then also a shift in the bottom, eta plus b lambda lambda. Okay, I just applied that shift. Now, you'll recognize one thing, which is that this has a term that looks like lambda times lambda, and that's 0. Okay. Now, if I just expand the two terms here, I have a piece where there's an a and it gets divided by a, and that's none other than just the original epsilon plus. But I have a new term, which is a to lambda, just some number, times p alpha alpha dot. Where did p alpha alpha dot come from? It came from the second term, which one is lambda and lambda tilde. Okay? So these two terms, this term and this term, just end up becoming these two terms. Now, of course, you'll recognize this as a gauge transformation on the external polarization. Okay? So what this means is you could choose one eta, choose a different eta. Whatever eta you choose is irrelevant, because we know that when we dot this into a Feynman diagram, so if you choose to construct your amplitudes that way, it won't matter. Okay? Now, obviously, this introduces a massive redundancy. I could pick any etas I want, literally any choice you like, provided that you can expand it in terms of these two guys, so there's no secret linear dependencies amongst them. But that is the place where the redundancy is input if you choose to use polarizations. Now, at the same time, polarizations are actually kind of nice because it shows you, at least if you're more used to the usual field theory way of describing things, it shows you the little group properties of the amplitude. Okay, what do I mean by that? Well, of course, every amplitude is simply multilinear in the polarizations. Right? You just take an object that's made up of p's, and then you dot it into these epsilons. And as we just stated, the p's are little group invariant by definition. So the only little group covariance can come from the polarizations. Okay, so this means that we can just read off the little group covariance of any amplitude trivially from what we know from field theory, from Feynman diagrams. But of course, it's just a way of deriving something which is just true about amplitudes, which is that depending on the spin of the external states, there's a little group covariance of the amplitude. What do I mean by that? Well, just take epsilon plus and ask what the little group does to it. And just by, well, let's just flesh this out a little bit more. For epsilon plus, lambda will go to, let's see, maybe I have this swapped. I forget whether I define t as this or this inverse. But the point is that these guys actually flip relative to each other. So if this guy goes as t to the minus, I think this is, yeah. This is minus 2, and this is t to the 2, epsilon minus alpha done. Okay, precisely because the weights of these lambdas and lambda tildes are kind of constructed to give you weight minus 2 for plus helicity and weight minus 2 for negative helicity. Okay. So what does this mean? This means that if I give you an amplitude that's just constructed from polarizations, let's say epsilon 1, epsilon mu 1, epsilon mu 2, epsilon mu n. Okay, this is probably the way you're used to computing things. In terms of Feynman diagrams, you would compute some object which has free Lorentz indices, and then you can contract it with a bunch of polarizations. Depending on whether you choose plus or minus, will give you a different little group weight for the overall object. Okay? And in fact, we can just write down what that statement is, which is if I give you an amplitude and I apply the little group to it, it simply gets a prefactor of products of these t's. Okay, it's absolutely manifest when we write it in terms of polarizations, but it's a general fact about the amplitude. So in other words, if we take A and we apply a little group transformation to it, then we get this times a product I of ti. Okay, so this is a generalization of this observation we just made, which is that for each leg, you should look at its helicity, hi. Depending on whether it's plus 1 or minus 1 in the case of vectors, or let's say +2 and -2 in the case of gravitons, or what have you, you should have this covariance property of the amplitude. Okay. Now, so this will be actually the crucial fact that we're going to use to constrain a lot of physics. It seems very innocuous. In fact, it's absolutely trivial if you use polarizations. But as you might imagine, we're now going to move forward and not use any polarizations and just compute from a different set of principles what the amplitude is, but with this as an external constraint. So this is going to be a constraint on the amplitude that we need to satisfy. OK. Well, let me mention one more thing, which is this seems, at the face of it, a little bit crazy, which is that saying the amplitude actually is covariant, which seems strange, because you think of amplitudes as invariant objects. But keep in mind that for real momenta, these t's are all pure phases. So if you care about physical things, then these phases will ultimately cancel when you compute physical objects. Okay. But studied as a complex object in and of its own right, we can always apply this as a rule that the amplitude should satisfy. OK, good. Any questions? OK, good. So let me now use the rules we've deduced to construct essentially all possible theories that can describe massless interacting particles in 4D. Okay, so the things we're going to use are this property of the amplitude, the fact that we can write objects in terms of spinors, and later on the factorization property of amplitudes. So we're going to start simply at 3 particles, where everything can be derived incredibly crisply. And in fact, we won't even need factorization. All we're going to use is Lorentz invariance and little group and show that the 3-point amplitudes for massless interacting particles are entirely fixed. And the kind of upshot to that is that what you thought was kinematics, what you thought was simply just ways of describing momenta, is actually entirely dictating the interactions. Yeah.
Yeah, so your discussion of little group, so you said that for real momenta, T is basically pure phase. Which
Yeah.
seems to be correct in the sense that it corresponds to SO2, and which
Right.
we're familiar with. On the other hand, we do know that the little group is actually two-dimensional Euclidean group, and from a field theory point of view, we had to do some special thing to contract down to the SO2.
Right, right.
So what's the magic here? We automatically get that SO2 structure without doing it.
Oh, I see. I think it's built into this. So the question was, usually when you compute the little group with a vector in 4 dimensions, massless vector in 4 dimensions, the actual little group is ISO2, which is a set of Euclidean isometries of 2-dimensional space. 2 of those are translations, and the other one is rotation, which ends up being helicity. And we usually, just by fiat, throw out the Euclidean generators because they generate a whole continuum of spin representations. I'm just assuming the same thing here. So I'm fixing to just the helicity subgroup of ISO2. That's right. So that's why everything here is kind of at the very start labeled by helicities and not by some infinite dimensional continuum spin representation. It's something you can consider, but I'm not going to be that exotic in this talk. Yeah. Any other questions? OK, good. So for 3 particles, we can do essentially everything just from kinematics. Why do I say that? Well, the fundamental relation that we care about is the sum of momenta sum to 0 at 3-point. And this translates into a relatively simple statement about the spinors. So you could take p1 plus p2 squared and realize that that's exactly p3 squared, which is 0, because I'm assuming massless for everything. But this guy, at the same time, is angle 1, 2 times square 1, 2. OK? And you can do this for the other combinations. OK? So in doing so, you'll find that there's a simple set of equations you can solve. Given that I'm running a bit out of time, I think, let me do this a little bit quickly. The upshot will be that we have a set of equations that look like 1, 2, 1, 2 equals 2, 3, 2, 3 equals 3, 1, 3, 1, and these equal 0. Now, if 1, 2 angle and 1, 2 square were complex conjugates of each other, so if I was restricted to real momenta, this would be very uninteresting because it would just mean that these are all 0 squared equals 0 squared equals 0 squared. But the beauty of complex momenta is that I can actually solve these equations in a more interesting way, where angle bracket is 0 and square bracket's non-zero. Okay? Perfectly fine. And then we can always think of that as an analytic continuation, which we can always take back to the real limit. Again, since I'm running short on time, let me just quote the solution to this set of equations. There's 2 solutions. Okay. I'll leave this as an exercise to you. One solution has all the angle brackets equal to 0, so all the square brackets equal to 0, which in turn means that they're all proportional to each other. So lambda 1, lambda 2, lambda 3, these are all proportional. When two spinors are proportional, their product with each other vanish because they're parallel. And then there's a second solution, which is that 1, 2 equals 2, 3 equals 3, 1. And that's just the statement that lambda 1, lambda 2, and lambda 3 are parallel. Okay, so there's 2 different solutions, which I'm going to name MHV and MHV bar, based on a kind of historical nomenclature referring to maximally helicity violating. I'm not going to describe why that was called that, but these are the names I'm going to give to these 2 kind of kinematic solutions to the 3-particle on-shell momentum conserving conditions. Yes?
You said something about how in the real case there's 2 exactly zeros.
Yeah, so in the real case, keep in mind that angle brackets and square brackets are just complex conjugates of each other. So for the real case, angle 1, 2 is just square 1, 2 complex conjugate. So this is just this absolute value squared equals 0. So it would be a very trivial solution, certainly, in that case. Yeah, sorry. Thank you. Yes. Good. OK, good. So now with this, we can now just construct the 3-point amplitude. We have all the machinery we need. And we do what is basically common practice in the amplitudes community, which is just to write down an ansatz and then constrain it. The ansatz is pretty restricted. Why is it pretty restricted? It's pretty restricted because let's say we pick, let's say MHV kinematics. Okay? I can only pick one of these. For MHV kinematics, all the square brackets vanish. So my amplitude can't depend on those. Okay, so that's pretty trivial. So we can only write down an ansatz that depends on the other brackets. So let's just write it down. So what is our ansatz? Well, let's write down an MHV amplitude. It depends on particle 1, which I assume to have helicity 1, particle 2, which has helicity 2, particle 3 that has helicity 3. Okay? So here's a key move whenever you start looking at amplitudes papers. No one writes down polarization vectors because we think of the actual helicities as labels of the external states, which they are. Right? You should label your external states not just momenta and a polarization, but with momenta and whichever helicity you actually care about. Okay? And in this sense, H1, H2, and H3 are much like flavor indices or some other index that you might imagine your theory has. They just label different states. Okay? Now they're related by CP, T to each other and so on, but they're still just states. Okay? Now what's the ansatz? The ansatz is the only thing we can construct from angle brackets, which I'll write as we only have 3 angle brackets we can construct from 1, 2, and 3. And I'm just going to put 3 arbitrary powers here. Okay? That's my ansatz. You could ask, wait, why didn't you write square brackets? Well, square brackets vanish. You would say, why didn't I add functions of p1 squared, p1.p2? Those all vanish. Everything vanishes. So this is the only thing I can even write down. Okay? You could write I consider that to be this n1 equals n2 equals n3 equals 0. So that's contained in the ansatz. Questions? OK. Now, the key point is that the little group fixes a constraint on these powers n. Why? Because we know that for a given helicity, this thing has to transform with some overall weight, which was given by that formula. Okay? So in particular, let me just write out equations. We can ask, consider the weight of particle, let's see, 2, 3. Particle 1. Well, the one spinner shows up with power of n3. It shows up with a power of n2. That's n2 plus n3. And that should be equal to minus 2h1, which is the weight given by that formula. Okay. And then we just do exactly the same thing for the other helicities. So 2h2 minus 2h3. And it's just a set of cyclic equations that we can just solve. Okay? So we can invert them, determine n in terms of h, and we get n1 is h1 minus h2 minus h3, n2 is h2 minus h3 minus h1, and n, so these are all h's on the right-hand side, and then n3 is equal to h3 minus h1 minus h2. Okay? So everything is fixed. The n's, which were unknown, are constrained entirely in terms of the helicities of the external legs. Okay. Questions about that? Okay. So let's just write down the final formula for the two cases, and then understand them in some different circumstances. Oh, let's see. Given that I have, how much time do we have? 10 minutes. Let me accelerate it a little bit. And just imagine, just plug these into this expression, and you have, well, I think I have to write this down, actually, unfortunately, because I'll use it later, which is that the MHV amplitude, a 3-point, is 1, 2, h3 minus h1 minus h2. And we can do the same thing for the other kinematic regime, which is MHV bar, where it's almost the same, except everything is replaced by conjugates. So rather than having this helicity, we have minus this helicity. Okay. Now, I wrote this down for a reason, which is that you could ask, well, under what circumstances do I pick MHV or MHV bar if I knew nothing about, kind of a priori, which kinematic configuration I was in? Well, here we use an extra clue, which is dimensional analysis. Okay? So we're talking about a 3-particle amplitude. So this is a vertex describing 3 things interacting. And it better be that it scales as a positive power of momenta, or 0 or positive power of momenta. Okay? In other words, these 1, 2s, and 3s have mass dimension. Right? Each one is effectively the square root of momentum. So it better be that the net mass dimension is non-negative. Because if it was non-negative, we'd be talking about a 3-particle amplitude that goes as 1 over derivatives, which is just patently nonsensical. So what that means is there's actually constraint on when each of these is applicable. And that constraint is that this applies when the total helicity is less than or equal to 0. And this applies when the total helicity is greater than or equal to 0. You can see this very trivially. Just add up, compute the mass dimension. I'll leave this as an exercise. Compute the mass dimension of these two objects, and just demand that they're positive or negative. And you'll see that in these two cases, it corresponds to the MHV and the MHV bar kinematic configurations. It can be 0. It has to be positive. It can be 0. So I should say, when I say mass dimension here, I'm only including the momentum-dependent mass dimension. So I'm not talking about the coupling constant dimension. I'm just talking about the dimension of the momentum factors. So it can indeed be dimensionless. OK, good. So that was a bit of work to derive something which we can now study. for the various cases of helicities 0, 1, and 2. And we'll actually learn some things. Okay, so let's take the case of scalar theory. Okay, I'm going to move a little bit faster here. For scalars, all the h's are 0. Okay, so it's very simple. In some sense, it doesn't matter which one we were talking about. The amplitude A3 is equal to 1, where by 1 I just mean not dependent on angle brackets or square brackets. Okay? Now, if I say this, this seems actually patently contradictory to what you might imagine, right? So certainly you can imagine an on-shell three-point amplitude that is 1 for scalars. Right? The canonical example would be just a cubic interaction, where again I factored out any dimensionful couplings. Those are irrelevant. But you could ask, wait a minute, there's lots of other scalar field theories I could talk about that just have more derivatives. Okay, so this guy's phi cubed. What about d phi squared phi? Okay, it has 3 phis. Just add more derivatives. Okay, some derivatives here contracting in some way. Now, of course, the point here is that if you actually compute the on-shell amplitude, you'll of course realize this thing can only depend on p's. Pi.pj vanishes because there's no Mandelstam and Variants at 3-point, exactly for these reasons that p1 plus p2 is p3. So in this case, you just get 0. Okay, so a better way of saying this is either 1 or 0, but nothing with kinematic dependence. Okay? So it actually accords with everything you know about any theory you could write down. Add 100 derivatives, add whatever you like, whatever complicated indices you like. There's no set of PIs that you could write down that wouldn't be 0. The only case where it's non-zero is for phi cube theory. Okay, so we've derived an important fact about scalar field theories, which is pretty trivial, but that's because we haven't used the weight of the little group quite yet. Okay, now let's go on to the case of Yang-Mills. I'm not going to call it I shouldn't call it Yang-Mills yet. I should call it a vector. So I really just mean a set of particles that interact that have not helicity 0 but helicity 1. Of course, the point here is that it's going to irrevocably take us to Yang-Mills with no freedom at all. But let me call this the case of vectors to start agnostic. Okay, so for the case of vectors, there's 2 objects we could write down. So just plugging into that formula I just wrote. And then the MHV bar. Okay. So let's take a look at this object. Okay. So I'm picking a certain set of helicities, minus, minus, and plus. I'll talk about the other ones shortly. But let's just study this object and ask whether it actually makes any sense. Okay. Now let's look at 1 and 2. So 1 and 2 are both minus helicity particles. Okay. And we're talking about vectors, so these are bosons. So I should be able to exchange them. I should get the same amplitude. Right? 1 and 2 should be symmetric under exchange. Okay. But we have a problem, which is that if you exchange 1 and 2, well, you'll get 2, 1 cubed over 2, 3, 3, 1. Okay. And keep in mind that, of course, the fact that this is an antisymmetric product means that if I swap the ordering, I get an opposite sign. Okay, so we're going to use that here. So you can see that I just get minus the old answer. Okay, so this thing acts like a fermion, the sense that it's odd under exchange. Okay, so that's just a contradiction. Okay, if I just gave you this amplitude and said there's some coefficient here, unspecified, but this is the amplitude, you'd have no choice but to make that coefficient 0. Okay, and in fact that seems unintuitive, but that's the answer. Okay. Why do I say that's the answer? Well, if I give you 3 vectors that are the same vector except one's plus and one's minus, and you try having them scatter in some way, 2 to 1, it's impossible because photons don't interact. Photons, there is no 3-photon coupling. It doesn't exist. The key point to remember is that when we talk about color, course, you have in mind that we should be deriving Yang-Mills, there's another index, which is the color index. Okay? So what I'm saying is there's two options. You can say, one, this is just 0, in which case you get the 3-point amplitude for photons, which is 0. Or you can introduce an extra complication. The only thing you can do when your amplitudes don't satisfy Bose statistics is introduce a new index which exactly conspires to restore that symmetry. Okay? The way we're going to do that is we're going to add an A1, A2, and A3. We're going to imagine that there's not just one species of vector, but some species parameterized by these color indices A. Consequently, this thing must have a coupling constant, which I'll call suggestively FA1, A2, A3, which depends on those species. Okay? Now, of course, the point here is that FABC is none other than the structure constants of Yang-Mills theory. And in order to maintain Bose symmetry, what we require is that this thing is antisymmetric in its indices. Right? So when you exchange 1 and 2, you have to remember to exchange the kinematics, but also to exchange the color index, because it's just another label on the states. In doing so, you will recall that this thing has antisymmetry properties, which exactly restores the Bose symmetry. Okay? Yeah?
Is this the source of the color kinematics duality?
This is not. Well, at least so you can see it actually when we talk about gravity, something looks reminiscent of it. But the color kinematics duality is, at least in my view, much more interesting, and I think something much more mysterious is going on. But unfortunately, or fortunately, it doesn't just end there for color kinematics. But we'll see that there's a very nice correspondence to gravity in this case. Yeah. So it's important because if I give you an object and say this describes the scattering of a set of bosons, then it better be that that object manifests Bose symmetry. If it doesn't act like a boson as a function, then you've written down something which is secretly 0 or inconsistent. Yes, so all I've really proven here is that A1 and A2 are antisymmetric. Yeah, so if you choose different LSDs, there's nothing in principle that tells you they should exchange because they're actually different states. Right? But we can ask about the other helicity. So let's ask about the other helicity, which is actually interesting. I'm going to talk about it briefly and then ignore it for the rest of the talk. Which, well, in fact, let me just draw it. Let me draw it here. Which is what about all minus? Okay, as an example. So you write down all minus. I'm not going to talk again too much about it, but it's of course interesting in its own right. Obviously, everything we write down should have some physical interpretation. For all minus, 1 minus, 2 minus, 3 minus, we just get 1, 2, 2, 3, 3, 1. Which you'll note is something which doesn't, if you didn't have, if you only had dimensionless couplings, wouldn't match the canonical dimension of a 3-point function. And the reason why is that this thing actually corresponds to the f cubed higher dimension operator in Yang-Mills. Okay? It's another object you can write. It's there. You can generate it by integrating out stuff. For the moment, I'm going to ignore it because I want to just think about the renormalizable leading order and derivative expansion of the gauge theory. Okay. But the upshot here was that there was no assumptions about gauge this, gauge that. It's just fixed. And we obtained a structure constant as an output of Bose symmetry, Lorentz invariance, and little group structure. Okay. Now let me discuss gravity as the last case. How much time do we have? Negative 3 minutes. All right. Well, I'll finish with 3-point amplitudes for gravity, and I'll have to save 4-point for my next lecture. But for a 3-point, the story is 3-point gravity. It's identical. In fact, it's very simple. Same formula. Except there's no issue with Bose versus Bose symmetry at all. For the case of tensors, you'll find that A3 of 1 minus minus, 2 minus minus, 3 plus plus, which is my notation for helicity minus 2, helicity minus 2, and helicity plus 2, is just the square, actually, of that object, which is 1, 2, 6 over 1, 3 squared. 2 squared. Okay, and likewise for same HV. and likewise for MHV bar. Okay, so this is, since I'm going to pause here, let me just make the case for why this is incredibly minimal compared to what you do, even at 3-point with Feynman diagrams. So if you recall how to compute the 3-point amplitude for Yang-Mills, it's actually a much bigger object, right? You're probably used to writing things like epsilon, 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 and then things with various contractions of eta mu nu, p minus pq, rho, etc. In the case of Yang-Mills, it's 3 terms, maybe not so bad. It collapses to 1 term, that's nice. In the case of gravity, famously, Bryce DeWitt wrote down the vertices you need to compute 3 graviton interactions almost 50 years ago, and I guess around 50 years ago. And the number of terms is something like 120. It's an insane number. Okay, it's absolutely enormous. So imagine taking each of those 3-point vertices and plugging them into a 4-point diagram, right? 120 squared terms, and so on and so forth. Clearly, you can see some elegance appearing, which is just the fact that these objects are incredibly simple, and they have, in fact, some nice relations amongst each other. So since I'm running out of time, I'm going to save 4 particles for next time. But as a kind of foreshadowing, what I'm going to do is take all these 3-point amplitudes and combine them with factorization to derive all massless field theories in 4 dimensions that interact. So I guess I'll stop there. Thanks.
Sorry.
Nope, it's 2. This is dimension 2, 6, so it's the dimension 6 operator.
Oh, right. I have a question about
Yeah.
these. They're using untitled these vector ones. Why
Yeah.
are they not all zeroed by just like angular moment conservation?
So you have to keep in mind that there's not only